So welcome everyone to our fourth and last session of this first edition of the WinC Seminar series. So we are very delighted to have Chloe Martindale. Chloe is a lecturer at the University of Bristol and doing research in post-quantum cryptography. Her main research interest lies in constructing, but also cryptanalyzing or breaking isogeny-based schemes. And I guess more generally, it's fair to say that Chloe is interested in everything in cryptography that is related to number theory. And Chloe works also in the dissemination of scientific knowledge. For instance, Chloe is part of the crypto panel of experts of CFRG. And if you don't know what this is, that was me 5 minutes ago. I think it's a good question to ask Chloe later. And then Chloe is also engaged at schools and public science events. And before coming to Bristol, Chloe was a postdoc in Eindhoven University under the supervision, let's say, of Tanja Lange. And Chloe did her PhD at the Leiden University in Bordeaux University under the supervision of Marco Streng. Well, and then I hope everyone enjoys the talk, and the floor is yours, Chloe.
Thank you, Katerina, for the introduction, and thank you to all the organisers for the invitation. It's amazing that you've managed to set up this network, and I'm delighted to come and speak to lots of brilliant women in cryptography. I was also asked, as well as the technical content, to say 5 minutes a little bit about my journey as a woman in cryptography. So let me start with that. So I think probably like most people in the field, there's been great moments and also terrible moments. So I didn't start off interested in cryptography at all. I didn't actually really know what cryptography was until quite late in my career. I did a degree in pure maths, and I was very interested in number theory. But for whatever reason in my degree program, there was no cryptography, and I was not interested enough student to go and find out about it on my own. I went to do a PhD in pure number theory, and sort of started to meet people who were doing cryptography. As you know, as you go through your PhD, you start to collaborate with people and find out a little bit more about it. And like started to become interested in it mostly as a I don't know if any of you have the experience of working in pure maths, but very few people care what you're doing, which I didn't find particularly motivating as a PhD student anyway. And I had really made wonderful friends during my PhD and had some really good times, but during the end of my PhD, I was not in a good place, and especially the sexism in the workplace was something that I found very hard to deal with. And if the postdoc with Tanja hadn't basically fallen in my lap, I definitely would have quit, which I'm sharing with you all, partly to let you know that if you're in that place, then things can be better. I was, I think, probably depressed. I didn't get a diagnosis, and I just hated it wasn't, I didn't get harassed or anything that dramatic, but I hated the everyday sexism of, you know, more junior male PhD students always being asked things before me, never being invited to give a talk in the local seminar, just sort of every day, the classic bad sexist old men always picking on the female speakers, picking up little edge cases that you got wrong in your slides over and over again, but not doing the same to male students. These sorts of things, which I hope not all of you have experienced, but perhaps that's unrealistic to say all of you experience. And that was very much my reality at the time. And I think I assumed it was universal, and I now know that that's not universal. So if you're in a position where you think that's universal, then go somewhere better. So I got my postdoc. I won't tell you the story because it's a very long story, but not through like applying for lots and lots of jobs. And I did apply for a few jobs and didn't get them. But basically through a friend who knew that Tanja was looking for somebody kind of urgently. And I hadn't really looked at that as an option because I wasn't doing cryptography. But it turned out that she was looking for somebody who actually knew a lot of number theory and didn't really mind if they didn't know cryptography, because that's not what she needed at the time. And I remember in my interview, she said, if you come here, you will become a cryptographer. And I was like, that's fine. I'm fed up with pure maths anyway. And she'd also asked if I had any questions. And at this point, I was so fed up with you know, the sexism that I was experiencing on a day-to-day basis. You know, I sort of told her a bit of what had been going on. And she said, well, that won't happen here. And I thought, well, at least, you know, I have the protection of a very fierce woman. So hopefully that will be a better environment. I thought, if I'm going to risk it, I'll risk it here. And well, any of you who know, you know, that was wonderful. That was protection that I needed and at the time. And she believed in me in a way that I didn't believe in myself. And that made all the difference to me working there. Not to say that I'm sure there are also arseholes at Eindhoven, but I didn't meet them. And I had a wonderful time there, and really got to become an independent researcher, and you know, she mentored me and helped me grow in a way that I needed. And then I was able to go off on my own and in an independent new place and talk to people about my experiences, rather than think, oh, I've got to hide this. So when the position came up in Bristol, I was still on the edge about going into academia, because I really did not want to go back into the environment I'd been in before. And Tanja was fighting to get a position for me in Eindhoven as well, so I thought that, you know, I've got something where I know I'll be in a good place. But I thought, well, okay, I'm going to try. And one thing I did, and I'm really glad I did, in the sort of negotiations with the position in Bristol, is I spoke to the head of school who was organising that negotiation, and I told him about my experiences and said, you know, if I'm going to uproot my life, get my husband to leave his job, move to Bristol, I want to know that I'm coming to a safe place. And I know you're not a woman, so you can't talk about your personal experience, but what do you have in place to protect people against that kind of thing? And they did have a policy in place, which really surprised me. I thought that I didn't really realize policies like that existed. And he was really supportive about it. And I thought, okay, well, if this is the head of school, I'll probably be all right. And I have to say that I've had a super positive experience here. And of course, that's probably not universal, and your seniority makes a big difference in these things. But there exist good places that will support you, and there exist bad places. And some people can be the trailblazer, and they can be the trailblazer who make it better for everybody. And you're amazing if you're that person. I am not that person. I can't be the trailblazer. I need the supportive environment. But these environments exist. So I guess that's what I wanted to say about my journey. I feel all emotional now. Now I have to try and give a technical talk, but there we go. So feel free to reach out to me about that, either in private or at the end. I'm happy to talk more about that. So now onto the cryptography. So this is a talk that, if you went to Eurocrypt last spring, you've already seen, given by other people, not by me. So apologies for that. All of us, especially the organisers, also don't really know yet who the audience is. So I'm going to try and make it accessible to everybody, but my apologies if this is just not your corner of cryptography, and you feel very free to tell me if you have any questions. I'll try and create space for that. And also apologies if you already know all of this and can't learn anything from it at all. So this is about isogeny-based cryptography, and I've said elliptic curves here because that's maybe something that's more familiar to people who don't spend all of their days thinking about post-quantum cryptography. Isogeny-based cryptography is just built from elliptic curves, although it sounds much more scary, and to be fair, it is much more scary. Okay, so hopefully this slide is something that everybody is familiar with. Let's start with Diffie-Hellman key exchange, and then think about how we can make that post-quantum. Right, so Diffie-Hellman key exchange, this is a cryptography seminar, so everybody knows what this is. What is it? I've just got a slide here so you can see how similar things are in the post-quantum world. So Alice and Bob are two parties who want to create a shared secret value that they can do cryptography with, whether that's AES or sending encrypted messages or whatever it might be. In order to do that, then they Alice chooses, let's be Alice. Alice chooses a random value between 0 and the size of the group, and raises an element of her group, a public element of the group, to the power of her secret to create her public key, gets Bob's public key, and then computes this shared secret here. And these two values should be the same. And the hardness of this crucially relies on the discrete logarithm problem. And I know Nina mentioned a little bit about post-quantum last week. So Shor's algorithm breaks this discrete logarithm problem on a quantum computer in polynomial time. So post-quantum cryptography is about, well, how do we solve the fact that this is no longer a hard problem? But I mean, there are other things in post-quantum cryptography as well, but the biggest problem we have to solve is this, really. There you go. My favorite stamp. Okay, so the problem is that in this case, this is not broken at the moment, but we expect this to be broken in the I guess medium to distant future or something along those lines, and we need to prepare for this reality that's coming up. Okay, so what can we do? So there are multiple things we can do. I'm going to talk about exactly one thing. Here's one idea. Right, so exponentiation is the operation that we're trying to replace. Right, so if you look at this equation here, this is a way of writing out what you're doing when you're doing a Diffie-Hellman key exchange. Is you take a group element, you raise it to the secret power x. Right, I've just said it's taken from the integers. Of course, you need to bound it by something. And the idea that was originally had by Jean-Marc Cuveigne in 1997 and rediscovered by Rostovtsev and Stolbanov in 2004. That seems like a long gap, but Cuveigne's paper was rejected and forgotten, so they definitely didn't know about it. The idea is to replace this exponentiation by a group action on a set. So if you know what group actions and sets are, then this is actually a very natural thing. If you don't, it's not very natural at all, I guess. But if you write this map in this way, that's basically all it is, except you allow this to be some other function that's not exponentiation. So let me write up what I mean by that. So you replace G by a set. So this is the crucial part here, because Shor's algorithm, and that is attacking like the structure of G. The fact that this is a group is exactly what Shor's algorithm is exploiting. And a set, well, you've removed the structure. So it needs to be a set that is not a group, crucially, or at least not a group where you can, with computable group operations in it. So it needs to be something with no structure. And we, Cuveigne and Rostovtsev and Stolbanov suggested a specific set of specially chosen elliptic curves over a finite field. And then they observed that you can have this group action where you replace the integers by some special commutative group H, which I won't go into, that acts freely and transitively via surjective morphisms. So let me say a little bit about what that is. So your set is a set of elliptic curves. So each element, instead of being an element of a group, which if your group is an elliptic curve group, then that would be like a point. Each element in the set is a whole elliptic curve. And so what's this H going to act by? Well, this needs to act by something that relates to elliptic curves to each other. And so that's going to be a map that takes one elliptic curve to another. It's a birational map. It doesn't really matter what it is, but it's a birational map, and it acts, and those things are called isogenies, and that's what this isogeny-based cryptography, that's what the isogeny part is referring to. And there's lots and lots of history in number theory studying elliptic curves, and so quite a lot of things are understood about this, and it turns out that this commutative group is something called a class group that we know a reasonable amount about, and we can use that for this construction. So this idea has been around for ages, but there's a reason that nobody was talking about it in 2004. Oh, so is that a question?
I have a doubt. Yeah. So like between these two elliptic curve groups, your definition, if it is non-trivial, it will be injective as well as surjective, right? Because of the dimensionality we are getting here. Or is it just a Z-module homomorphism between the two elliptic curve groups you are defining? Whatever the group of Group action or the morphisms you're saying as isogenies?
Okay, it broke up a little bit, so I'm going to try and fill in the gaps. So the question was, what exactly are these surjective morphisms?
Yeah.
So if you think about, if you've got two elliptic curve equations, right? So your y squared is x cubed plus ax plus b, and y squared is x cubed plus cx plus d, right? So they're both, they're more than a group, right? So there's two things. There's an equation which is defining an algebraic curve, and also the set of all the solutions to that equation together with the point at infinity, which forms a group. And so the map, the isogeny, that needs to preserve two things. It needs to preserve the fact that it's an algebraic curve, and so that's going to be a sort of birational map, so quotient of functions. Well, I think I might have an example a bit later. We'll get there. And it also needs to be a group homomorphism, which is perhaps something that's more familiar to people who've worked with classical elliptic curves. Yeah. And so I see where your question comes from. Like, what do you mean it's just surjective? If you're thinking about only the solutions over like a finite field, then this doesn't really make sense. But the set of solutions to the elliptic curve, you can define that over a finite field. You can also define it over any extension of that field, all the way to the algebraic closure, which is then an infinite field. And so it needs to be surjective on the group of points over the infinite field. And then it can be injective, and then it's an isomorphism. But it can also be not injective. It can also have a non-trivial degree, but it does always have to have finite kernel. And that size of the kernel, in most cases, is also the degree of the map. Is that clear?
Okay. Yeah, thanks.
I feel like I need a whiteboard, but that's hard with also slides. Thanks for the question. Any other questions about this?
No, thanks.
Okay, great. Okay, so once we've got this setup where we've got this new group action, then we have something called the Kuvenyi-Rostov-Stolbanov key exchange, or CRS for short, which hopefully, if I've drawn my picture correctly, looks very similar to the Diffie-Hellman key exchange we had before. So our public parameters look slightly different, right? So now instead of a group, we've got a set, and each element in the set is an elliptic curve. And instead of choosing a base point G of our group, we choose a base elliptic curve, E. And then we've got this mysterious group which acts via these isogenies that we've been just talking about. Okay, so then our Diffie-Hellman key exchange, what does it look like? Well, it looks very similar. Right, so let's be Alice again. Alice chooses a random group element, where before she chose a random integer that was smaller than a certain bound. She acts by her group element on her elliptic curve, and that's her public key. And this thing here, because it's a group action, that will also be an elliptic curve. So her public key is a different elliptic curve, not E, but some other one that's Alice's. She sends that to Bob. She receives the same thing from Bob. And then she computes a shared secret, which, so this B star E, that's going to be an elliptic curve in the set. And she can also act on that with her element. And because of the way that group actions work, if you can sort of move the brackets around. So both of these secrets, so this one will be A times B acting on E, and this one will be B times A acting on E. And of course, you need a property here, right? You need that the group H is commutative. If this H is not commutative, then this is not going to be the same value. This is actually quite important, as we'll see later. And then your discrete logarithm problem is replaced by this problem here, which is finding A given E and A acting on E. That should be the hard problem. So this is the sort of equivalent of your discrete logarithm problem. Any questions on that? Okay. So again, I'm not talking about my research yet, right? I've only talked about what other people have done. So this is still from 2004, and it's a really beautifully mathematical construction, but I think Rostov and Stolbanov wrote an implementation, and it took something like 20 minutes for one key exchange. So that's not ideal, obviously. Well, I think maybe I have a history slide in a minute. Let's have a look. Yes, here we go. Right. So let's see. Well, where do I come into the picture? I suppose seems a bit egocentric, but I'm giving the talk, so there you go. So in 1997, I already mentioned this, Cuvenier proposed this scheme for the first time. Don't worry if you don't know what this means, but it uses the set of elliptic curves that he chose to try and use were called ordinary elliptic curves, which are the ones that are used in, so for example, curve 2519 is an ordinary curve. So most things that are used in classical cryptography nowadays are ordinary because actually the supersingular cases, which is the other case, is kind of broken for the discrete log. And then this endomorphism ring, again, don't worry what that means, but it basically is controlling this group H that's acting on the set. His paper was rejected, and he promptly forgot about it and went to do something else. So Rostov and Stolbanov rediscovered it, and at the time, the best known attacks, both quantumly and classically, were exponential. But 1 year later, Kuperberg came up with a way of applying Shor's style ideas. So Shor's algorithm, again, that's the thing that solves the discrete logarithm problem. And the way it does that is by solving something called the hidden subgroup problem in an abelian group. And if you know anything about sort of the theory of finite groups, then perhaps you remember that sort of the next thing you could try and do after an abelian group is a dihedral group, which is not very far away from an abelian group, but somehow already this difference makes it a lot harder to attack this hidden subgroup problem. But Kuperberg came up with a way of doing a sub-exponential attack on the dihedral hidden subgroup problem, which his motivation was not to break CRS, because that was something that not many people knew about. And it's also one of Kuperberg's algorithm is also crucial for like estimating the complexity of lattice algorithms, for example. So it comes up in all sorts of places. But a few years later, Charles Zhao and Sukharev noticed that his algorithm did apply to CRS as well. And then if you sort of made a very approximate guess as to how this algorithm would apply to CRS to get 128-bit security or 64-bit quantum security, then you're looking at a key exchange of about 20 minutes. And this was actually, David Zhao says, I've heard him say in talks a few times, this was his motivation in developing SIDH, which I think I'll tell you a little bit more about it because I'm going to tell you how to break it later. Together with Luca De Feo, which I think spurred a lot of research in the isogeny community. Like this was the focus of most people working on the field for the last 10 years or something, and was the precursor to Psych, which was in this competition, and got all the way to round 4 before being completely broken. And then in 2017, Luca De Feo, same person, and John Kiefer and Ben Smith, for John Kiefer's master's project, they went back to look at this CRS key exchange basically for fun, and tried to do some very fun number theory to try and get this time down. And they did a lot of work to get it down to 8 minutes. And me and Lawrence Pani, who's here, who was a PhD student in Eindhoven at the time, I was a postdoc, we saw this work and thought, oh, that's fun, let's have a look at that. And we needed something to do at one of these research retreats in Tenerife, because Tanja had some money to use up. And we thought, well, let's look at this and see if we can make it faster. And well, what we realized is that, so we thought about lots and lots of ways of trying to make it faster. And I think the day after we left or something, Wouter sent everyone an email, Wouter Kastrick, saying, is there a reason we're not using supersingular curves? Because they have all the properties we need. And we were like, no, there isn't. So then we realized that this other type of elliptic curve basically just makes everything work super trivially. And then lots of other fun things came out in the wash as well. It's one of these sort of serendipitous research moments when everything just works out well. And so then this 8 minutes came down to 60 milliseconds. So these are the numbers that I think are fair to compare. But then because it became fast enough to be practical, people put a lot more work into figuring out the best way of applying Kuperberg to the scheme and these things. So I think 60 milliseconds is maybe not an accurate number for how fast you can expect this to be for secure parameters. But in terms of comparing it with what was there before, this is the speed up that you get. There are now other ideas around about how to do CRS in efficient ways. For example, you could do it over a binary field. I know there's a few people looking at that. And then that also might be quite efficient. So that's this is pronounced seaside, in case anybody's wondering how to pronounce that, because we did it in Tenerife at the sea. And it was sort of that's one of the things that we can still do with elliptic curves that we believe is secure in a post-quantum world. Here's a picture of a seaside to make you all feel happy. So I wanted to, I don't think I put a slide on this, so I'll just say it in words. I wanted to say a little bit about, now that I've told you what seaside is, not just for seaside, but also for isogeny-based in cryptography in general, why it's something that I think is a nice thing to look at and why people look at it in the community. And also why the things you need to be careful with. So perhaps you already got an idea from this a little bit, but it's, compared to things like lattices, it's quite slow. So I think the best things are about 1,000 times slower than lattices, but they're also about 1,000 times smaller than lattices. So things like ski sign, which is in the NIST competition, the new NIST competition for signatures, parameter-wise, it's just the best choice, but it's also mega slow. So ski sign is a signature scheme that's based on isogenies that, of course, was invented at a ski resort because that's how we do our things. So it's this sort of this trade-off where if you have something where size really matters, so my favorite example of the moment is if you want something to fit in one package, if you're sending something over patchy internet because you live in a place with patchy internet, and you might get security problems from cutting up your huge Kyber key into loads of little bits and then trying to piece it together, or dropping packets and malicious people putting malicious bits in the middle and this kind of thing. Then if you want post-quantum security, isogenies are not just the best choice, but actually the only choice, because you want it to fit in this packet. It's all you can do, actually. So I think it's really worth trying to solve these speed problems in order to have something that's going to fit there. So the size is the main pro, but there's other pros as well. So one is flexibility. So in terms of the sort of applications that people have come up with for isogeny-based cryptography, partly because you've got this Diffie-Hellman style non-interactive key exchange from Seaside, are vast. You can do a lot of things that you can't do with anything else. One of them being non-interactive key exchange. And something that you probably won't expect me to say unless you know a lot about the field is actually security. So people's confidence has been knocked in isogenies after breaking Psych, which I totally get, because people who weren't in the community had a lot of faith in Psych. But the faith, like a lot of things in cryptography, is mostly based on politics rather than maths. I think for something like ski sign HD, which I'll talk about a bit later, well, not really, but I'll mention it later, which is a version of ski sign that actually uses the mathematical techniques that we've rediscovered in these attacks on Psych, has a really, really nice security reduction to a very old number theory problem, which is something that would be really, really hard to break. So there are, once people have sort of got over the politics of Psych, which will happen at some point, people get over these things. I think it's something that I have, personally, I have a lot more confidence in that than some of the other things that people might have confidence in, but that's very much a subjective view, of course. So a con is obviously confidence from other people in these schemes. And the complexity of the schemes is also a big con. So they're extremely complex. If you like, the NIST requirements to have a submission in C was a huge problem for the ski sign team. They had to work for months on this with a huge team of people and keep adding people to the team in order to make the deadline. Whereas for something like Mayo that maybe Sophia has talked about, I'm not sure. This was something that, you know, you can do in a much more doable way. There's just like, it's something that way more people can check, and it's much easier to get to something that you can believe in as a secure package of code. And the complexity of these schemes of isogeny schemes is just huge compared to some other things, and that's something that's definitely a big downside. Okay, good. All right, sorry. So I should have made a slide about that, but I didn't, and I remembered 5 minutes before, so I didn't have time to make a slide. Good. So let me talk about where to go from there. So evolution of key exchange, right? So here's my Diffie-Hellman key exchange again, which I've written in a different way, which if you look on Laurent's whiteboard behind her, you might see why I've written it in this way. Right, so we already said if you've got a Diffie-Hellman key exchange, you can slightly change your parameter setup and you've got seaside, right? These are very, very similar. Now, in order to explain SIDH, we need to think a little bit about what these arrows actually are. So I should probably say, so these stars, right? I wrote these stars because that's what you write for a group action, but we could actually just drop the stars because I told you they're functions, right? So alpha is a function of E0 or a function of EA or sorry, EB or whatever, right? So these are functions. Now, how do we compute these functions? Well, we compute them from their kernels, right? So we go back to thinking them as group homomorphisms, which is perhaps a happier place for most of you anyway. It turns out that these functions are uniquely defined by their kernels. So if you know the kernel, then you're done. And actually this if you look at the kernel of alpha, so alpha was Alice's secret, the orange, oh, I've written down here, the orange is Alice's secret. The kernel is a cyclic group that's generated by an elliptic curve point A. And so that is also Alice's secret. It's an equivalent way of writing Alice's secret. So what's the kernel over here? Because this elliptic curve point A is on E0. And this is supposed to be a map from EB. Well, that's fine, because we can just map it under beta, Bob's isogeny, to EB. And then we know, and then that turns out to be the kernel of Alice's isogeny. Now, that's all well and good, except how on earth does Alice know beta of A? Because she doesn't know beta. She knows A, but she doesn't know beta. So she can't compute beta of A. And this concept is actually how to solve this problem. This was the revolutionary idea that David Zhao and Luca De Feo had when they invented SIDH. Also turns out to be the downfall of SIDH. Okay, so in order to explain that, let me tell you a little bit more about this this A. So we know quite a lot about this point, this kernel point here, A. The torsion, we know we can write the A torsion of E0 as generated by PA and QA. So we can sort of choose our kernel point by just choosing this one little number A here. And actually, we can make this PA and this QA public. We can make those public because that doesn't reveal any information. As long as there's enough choices for this little A, then you've still got, you know, enough choices for the big A. That's the idea behind it. And then the idea behind SIDH is that you don't only share the public point. Well, let's do Bob's. You don't only share the public elliptic curve, but you also share the image of these public points, PA and QA, under the secret isogeny beta. And then you hope that revealing that information about beta doesn't give the adversary an advantage. And for a long time, there was no idea or only some idea how to do this, but not anymore. So just to go back a second, so the key thing to notice about SIDH, I think, really is that, so you've got these public curves, and if you're just thinking of like seaside or a natural generalization of Diffie-Hellman, that's all you'd have. you don't also reveal a bunch of information about the secret, right? So you're actually giving away, it looks like you're giving away way too much. But I mean, I thought about this for 5 years and couldn't figure it out, but it's not obvious, but you are giving away too much, it turns out. And it's something that I think a lot of people who are in the community definitely hadn't given up on trying to exploit that information. So, okay, how do you use this information? I think I have another history slide now. Yeah. Well, this isn't a history slide, but so what are the hard problems that are going on here, right? So again, first and foremost, Diffie-Hellman, something you're all familiar with, discrete logarithm problem. Replace the discrete logarithm problem with your CRS or C-side. That is, find this group element given the action of it on an elliptic curve. Another way of phrasing CRS or C-side, and something that is a hard problem in all isogeny-based schemes, is given two elliptic curves, compute an isogeny between them. Right, and this is only slightly different from the problem that needs to be easy, which is given one elliptic curve, compute an isogeny from it to the endpoint. And then the hard problem needs to be recover the right isogeny between these two elliptic curves, or actually any isogeny will do. Now ISODH is a lot more complicated, right? So you're given this secret isogeny between these two elliptic curves, but you're also given 2 points on the first elliptic curve and the image of those 2 points under the secret. And then you have to compute alpha. And then ignore this small text at the bottom if you don't know anything about elliptic curves or going a bit too fast. I should have paused for questions on the last slide, but I didn't. Are there questions now? No?
I actually have a question.
Oh yes.
Sorry. Is there any a priori condition on the points PB and QB? Like, can these be any points, or maybe it's in the small text below? But like, I mean, I guess like depending on what points you use, maybe this also leaks more information or less information.
Yes, it's a good question, and it is in the text below. So the if you don't know about the latest attacks from last year, then if the order of the points PB and QB is not co-prime to the degree of alpha, then this will reveal as much as is not co-prime about alpha. And so part of the way that they set this up is that they chose PB and QB to make sure that the order would be co-prime. And actually, in order for this all to work out, you need more than that. You need them to generate a torsion subgroup. So if you look at the small text below, you see there's actually an equation that says PB and QB are the generators of the n torsion subgroup of E0, and n will be a specific choice. So yeah, they're very specially chosen points, chosen in order to try and avoid leaking information, but it turns out that actually any smooth n will leak everything because of the reasons I'm going to go into in a minute. Okay, so this is the hard problem that people who were working in the field were trying to attack for a while, with this very sort of specialist hard problem that has different names in the literature. And so this problem was, of course, first introduced by the authors of SIDH, Luca De Feo, David Zhao, and Jérôme Ploux, who's sometimes there and sometimes not. I'm not sure what's going on there. And the first time that anybody came up with any way of exploiting this information was already 5 years later, which was Galbraith, Petit, Shani, and T. And they gave an active attack, which recovers 1 bit at a time by basically using malicious choices for PB and QB. So this is another answer to Katerina's question. And because even though they have to satisfy these equations, there's actually still many choices. So you can use malicious choices, you can also use malicious secrets, and they give an active attack, which meant that this couldn't be sort of a drop-in Diffie-Hellman like C-side is. You had to sort of turn it into a chem with a Fujisaki-Okamoto transform. And that's part of the version that became Psych eventually. And then 1 year later, Petit sort of extended this extended this method is not fair. He gave some new insights which allowed a passive attack on this problem. So let me just go back a slide and remind you, like, this problem, I haven't made any sort of assumptions on size or balance or, you know, Alice and Bob doing roughly the same computation. This is stated in a sort of very general way. And that's on purpose so that I can talk about the various attacks that came up. So the first attack that Petit came up with, it attacked some parameter sets, but it needed sort of parameter sets that would make no sense. So Alice and Bob would both need to compute secrets that are way bigger than you'd need in order for security, and Alice's secret would need to be way bigger than Bob's secret and things like that. But it was still very interesting because it showed that, you know, it's not as hard as the pure isogeny problem. And then basically since then, me and Lawrence Pani and Christoph were thinking about extending this. And then we also started working with Peter Kutas and Victor Cohen and Chris Leonardi and Kate Stanger. And we came up with a few different ways of extending those attacks. And Peter Kutas also came up with actually a really new way of attacking it on more parameter sets. Still not the psych parameter sets, but we'd already got quite close. So like we basically showed that unless you choose exactly the parameter choices they make in psych, then the complexity of the meet in the middle attack is higher than the complexity of any of these sort of Petit style attacks. And then I guess we gave up and decided to publish the paper there. It was already very long and complicated. And then a couple of years later, so Luciano Maino, he's a PhD student with me in Bristol, and he was working on some genus 2 stuff, and he got a bit stuck on his project, and oh no, sorry, I should say first. So I went on maternity leave. I have a child who's 2 1/4. So a lot of you have met him, so you know this. He comes to all the conferences. I went on maternity leave, and Luciano went to Leuven for a couple of months to entertain himself, and chatted with Wouter Kastrik and Thomas Decru while he was there. And they were all interested in esoteric dimension 2 stuff. That's elliptic curves plus crack also. And they were thinking about verifiable delay functions and all sorts of crazy things. And then he came back to Bristol, and I came back off maternity leave, and he was a bit stuck on both of the projects he was working on. And he said, "Oh, can you give me something else to think about? Because I'm a bit frustrated." And I was like, "Yes, of course." And I said, "Read this paper that I wrote in 2020 and see if you can come up a way of sort of formalizing the limit of this method so that we can make an argument that psych really is secure." And he said, "Okay." And then he came back to me the next day and said, "I think I have an attack." And I was like, "Oh, sure, I'm sure you have an attack. Let me think about it." And so then I spent a couple of hours looking at it. I was in Edinburgh, because I was teaching on a summer school where Katerina was also there, I think. And the next day I was giving a talk about isogeny-based cryptography, teaching it to these students. And so I was giving this talk, and I was like, I know this is broken, but I can't share this information yet, so I'm gonna have to pretend it's not broken. It turns out Luca also knew it was broken, who was giving the other talk, and neither of us knew that it was broken. And anyway, it was all very fun. Anyway, so the ideas that Wouter and Thomas and Luciano had been working on for a different reason turned out to actually be a key in this relating these seemingly unrelated points to the isogeny. And Luciano wrote to Wouter and Thomas, but they'd actually come up with it themselves 2 weeks earlier and already messaged the site team. So we ended up writing the papers in parallel. So that was all sort of a very crazy time. And then once we put it online, then Damien Robert realized how he could actually attack everything in polynomial time, which at the time wasn't super obvious from the beginning. And lots of people got involved because it was all very exciting. So Lawrence and Jacques, that's Pani and Pope, implemented the attack, and Benjamin Veselovsky also came up with another method, and Anyway, it's most of you probably remember this, so I won't go into all the details. But basically, there was a lot of work, and people realized that this one theorem from Carney from the 90s basically gave the key between relating these two things. And let me tell you a little bit about how that works. I'm sorry if this is, I'll try not to make it overly technical. All right, I say that and then I say technical interlude. So there you go. If you know a little bit about elliptic curves, that's hopefully enough for you to follow. And I have tried to make it accessible, but it is very number theory-ish. Okay, so this is a reminder of what the problem is we're trying to solve. This is the problem underlying SIDH. And you see there's a big gap here. And that's because if you remember, I made this passing comment, so you probably don't remember if you don't already know it, that said, if you know computing the isogeny alpha is equivalent to computing its kernel, right? And its kernel we can all think of as a subgroup, and then we're all in a happy place where elliptic curves are groups again and not algebraic curves. Okay, again, the set of points in elliptic curves forms a group. The set of points on order dividing n is something that I've written in this way already in the talk. And all of these technical restrictions that I've not written down again here imply that actually we know exactly what this set of order n is. It's generated by the image of the public points for Bob under alpha secret isogeny, and these are exactly the things, if you look up here, that are shared in SIDH. So we know exactly what this is and like how Alice and Bob will be thinking about it. Now, the key thing here is if the degree of an endomorphism, so that's an isogeny from EA to itself, is equal to n, this n that is public and chosen by the scheme, then in fact the kernel of this, and remember the kernel is the same as knowing the isogeny, is inside this thing that we know completely. So you want to try and construct an n maybe, or a theta. No, n is given. You want to try and construct a theta where your kernel is going to be inside this thing. That's the idea behind Petit's idea behind the original attacks. There's another key thing you need to know, which is every isogeny has something called a dual, which is just a uniquely defined isogeny going the other direction. And if you know that, then you know the other, you know that kernel, you know the other kernel. And Petit's idea, to write it now down, is to construct a special theta from EA to itself. EA is public, but you don't know how to construct maps from EA to itself. That's a hard problem that's actually equivalent to the other hard problems. But if you can construct this special one, which is inside this, if you can construct the special one that's inside this thing that we do know, then you try and get the kernel of your secret in the right place. Okay, how do we do that? Here's a beautiful picture for you. Right, so green is public, orange is secret to Alice. Alice knows a secret, alpha, we have to find it. She also knows this special dual thing that goes back. E0, we make one restriction. We assume we can choose as many maps as we like from E0 to itself. This is a huge restriction, but it applied to psych because of other reasons. Then we can construct maps theta from EA to itself just by joining up all these arrows together, right? We know these images because that's given to us in SIDH, which means we know the degree of theta. And restriction number 2 says, if you can solve this equation, then you're completely done. That's it. That's the whole attack of Petit. But it turns out this restriction number 2 is exactly what gives you this restriction on these parameter sets. And it completely rules out the site parameters because of just by sort of serendipity, I guess. But enter Carney. So the problem is we don't have the theta of the right degree. So the solution that Luciano originally thought of was, again, he was playing with dimension 2 things for fun. You can take products of elliptic curves as themselves. This isn't the same thing as product groups. This is something that's really using the algebraic curve stuff. But there are group structures on these products, which are much, much bigger than just the product groups. And so you somehow got a lot more space in there. And Carney's theorem that everybody is using, they actually tell you, they construct everything you need. So you're given exactly this information, and Carney's theorem will construct for you E1 and E2 and an isogeny that goes between these two things, which will and that will absolutely completely reveal an isogeny, the isogeny that you need. And I think I've even written it down on the next slide. So how do we do this? This is what we started with before. Now, instead of having a map from E0 to itself, we have a map from this. We construct an E1 and a phi. And then Carney's theorem constructs everything in this picture. And so this isogeny here, this is the isogeny that Carney constructs. And so phi goes from E1 to E0 minus alpha hat goes from EA to E0. This has all the structure preserving properties you need, and Carney's theorem tells you what the kernel is. That's the key part. The kernel is the degree of alpha times all of the n torsion points on E1 and f of p. F is phi composed with alpha. Now, we don't know alpha, but we do know alpha on the n torsion. That's exactly what we're given. So we know the whole kernel. If we know the kernel, we can compute the isogeny. So we can compute phi and read off the secret. So in a way, it was, once you know the theorem and you've understood it, it's almost trivial, and it seems obvious in hindsight, which are always my favorite kind of results. And then a little comment is, okay, so this is the, I'm really describing Manu Luciano's attack here. It's not very different from Wouter and Thomas's, but it's a little bit different. And Damien generalized this attack to dimension 8 because dimension 2 wasn't hard enough. And then it turns out that you kind of solve all of the problems, but it looks very, very similar. He just takes lots and lots more products of elliptic curves, reveals things in exactly the same way, but then you've got a lot more choice for this phi. And that was a problem for me and Luciano, was the choices for that phi. Okay, so I've got a couple, just 2 minutes or so to tell you what's happening now and what's going on. So Boris Schwarzer, Tomoki Moria, and Christophe Petit came up with some mitigations for these attacks. And essentially, it either hides the torsion point images or the degree. And hopefully, it's clear-ish that those are, if you know those things, then the attack works. But if you don't know one of those two things, the attack doesn't work. They do make psych unusual, like completely slow and huge, and not attractive anymore as an option. But if you remember, one of the things I said is a pro about isogenies is that they are they give rise to a lot of things that actually we don't really know how to do otherwise, or maybe we only have one other way of doing it or something like that. So one example is Andrea Basso's oblivious pseudo-random function construction, which uses psych, and for a post-quantum oblivious pseudo-random function, it's still pretty good. But that's the disclaimer there is a big one. And cryptanalysis is very much ongoing effort. And so a group of us who were at the isogeny school in summer, not school, workshop, we are still trying to break it. And I still think it might be possible. So don't bet your eyes on it. But I think the most exciting thing that's come out of this is a huge boom in constructions and things that you can do with this trick that people now know about. I won't say it's a new trick, it's an old trick, but it's something that we now know about. So Festa, so this was developed by Luciano and Giacomo Pope and Andrea Basso. So it's a new PKE scheme. It uses the trick that breaks psych. It might, I mean, I'm not saying it's not going to get broken. I hope, I hope for them it doesn't, but some of the attacks that might apply to M side, as it's called, this masked SIDH, might apply to Festa. But so far, I think it has a reasonable hope of, once people have optimized it, as being as fast and small as psych was before the attack. And it's also caused a huge amount of research in the community in computing dimension 2 isogenies and dimension higher dimension, which is sort of problems that the computational number theory community have been stuck on for like 10 years. So that's been really exciting from that side as well. SkiSign HD I already mentioned. So this is something like a way you can adapt SkiSign to have more trade-offs, and it's very small and it's pretty fast, and it's got a much cleaner security. Let's say the security assumption for SkiSign is somewhat ad hoc, and for SkiSign HD it's not. And that uses this trick, and is something that can now be implemented as of a month ago or something, that uses dimension 4, and it's very complicated. The VDF that Luciano and Toma and Wouter were originally working on, and many more things to come. So something that I know about because I'm somewhat involved is Luciano and Damien and myself are working on a way of applying these ideas to compute things in number theory that nobody's managed to get a working implementation of, and the like. So that is all, and I think I'm also out of time, so happy to take questions, but appreciate it if you need to run off.